So we're talking about thermodynamics now, and I'm going to do a quick review of what we learned last time. There was really a lot of information in there, and we need to, I would say that's the hardest thing about this subject is that there's so much information that we learn in such a short period of time, and it can become a jumble, all of the, like, what's the difference between all of these different formulas and all of that. So basically, we're starting with the first law of thermodynamics, delta U equals Q minus W, where the W is understood as the work done by the gas. And for the work, we get the integral of P dV. So we're basically finding the area underneath a line in the PV diagram. And the PV diagram, is sort of the central tool. Almost all of our problems are just expressed as a diagram. Okay, we see a diagram and then that's it. Maybe we have a process that looks something like this, in which case the total work is the area enclosed in that shape. If we have a complete cycle, then the change in internal energy is zero because, for a cycle, we have these isothermal curves. And if we start at, let's say, point A on a cycle and go to point B and then point C and return to point A, whatever was the temperature at point A when we started, it's still the same temperature. And so since the temperature hasn't changed, then the delta U for the complete cycle is zero. And that means Q, kind of the net Q equals the net work. So if you add up all the Q's from every leg of the cycle, it adds up to all the work, which of course is just the area enclosed. So that's a point I didn't really make last time, but our formula for U is NCV. Well, I guess we have a formula for DU, NCV dt, or we could express it in terms of delta U, which would be NCV times delta T. So as you can see, if the delta T is zero for the cycle, then the delta U is zero. And for every cycle, delta T has to be zero because we wind up returning to our starting position. So that's always, right? Doesn't matter if it's constant pressure, constant volume, constant temperature, adiabatic, whatever. Always delta U only cares about the change in temperature. And we also learned about these different processes. We have isovolumetric, which just basically looks like a vertical line. And for that, we have the work equals zero, and so Q just equals delta U, and that's equal to N CV delta T also. We have isobaric processes. So for an isobaric process, that's a constant pressure process. Looks like a horizontal line. If we're graphing P versus V, we only graph P versus V. And so the work is just P times delta V. Instead of having to integrate, the P is a constant, so it pulls out of the integral. And Q then becomes N times Cp delta T. And, Cv, let's put this up here, is 3/2 R or 5/2 R, depending if it's monatomic or diatomic. And Cp is always Cv plus R. So then that would make it be either 5/2 R or 7/2 R. And then we had isothermal. So isothermal is delta T equals zero. So that means delta U also equals zero. And we worked out the integral for the work. It's just nRT times the natural log of V final over V initial. And we also know that Q is equal to W since delta U equals zero. So those are our three iso cycles: constant volume, constant pressure, constant temperature. And then we had, not cycles, processes. And then we had a fourth process called adiabatic. And for adiabatic, we know that Q equals 0. And so delta U equals, minus the work. And the graph looks something like this, where isothermal curves are similar but not as steep. And what we proved last time is that the shape of that curve is PV to the gamma equals a constant. So if we want to integrate it at some point, we can, okay, because we know the shape of that curve. And that's kind of what we stopped with. Today, we're going to practice doing cycles and finding the efficiency of the cycle, finding what's the heat input and what's the net work. And there's a lot of different cycles. All right, let's, I guess last but not least, let me define the efficiency as the work, the net work over the heat input. Okay, that's the definition. So we're going to take just a sample cycle. It starts with 1 liter of gas at 1 atmosphere of pressure and 300 Kelvin. And then it's going to go up to 4 atmospheres along a diagonal straight line while the volume doubles. So we go to 2 liters. And then it's going to drop down isovolumetrically back to 1 atmosphere, and then it's going to compress isobarically back down to 1 liter. And we're going to find the network and the efficiency. Let's call it E for this cycle. But there's a lot of information we need to kind of gather on the way to doing that. So first of all, we need to know if it's a monatomic or diatomic gas. Let's assume it's diatomic. And we, in general, don't need to find the number of moles, but if we don't find the number of moles, we have to do a lot of sort of gymnastics on our equations to translate temperatures into pressures and volumes and things. So let's go ahead and just find the number of moles and find the temperature at each vertex of this before we do any actual calculations. So if we label the points A, B, and C to find the number of moles, does anyone remember how we find the number of moles? Anytime we don't know something, there's just one formula we always go back to. Whenever we feel like I don't know how to do something, the very first thought should be which equation?
Is it PV equals nRT or whatever?
Yeah, absolutely. That's it. That's always when it feels like I don't have enough information, that's what I'm missing. So PV equals nRT. Now this is true at any point, so let's just put it at point A. And then the number of moles would be PA/VA over R times TA. And we need to put all of these pressures and volumes into the metric units. So 1 atmosphere is 1.013 times 10 to the 5th pascals, and 4 atmospheres is 4.052 times 10 to the 5th, just multiplying that first number by 4. And 1 liter, 1,000 liters makes a cubic meter, so we divide this by 1,000, we get 0.001 cubic meters and 0.002 cubic meters. So that's kind of, we need to do that. Often we get numbers in atmospheres and liters because it's easy, but then when we do calculations, we need to convert those. And so putting our numbers in, PA is 1.013 times 10 to the 5th, and VA is 0.001. The value of R is 8.31, in chemistry class, they keep pressures and in atmospheres and volumes and liters sometimes, and they just give you a different value of R with different units. That works, but we're not going to do that in this class. And then TA is just 300 Kelvin. So when I put all of those together, it's 0.041 moles. So some problems might just give us a number of moles, and then we have to find the initial temperature. If we're given the initial temperature, we can use that to find the number of moles. Now we can find the temperature at point B by just using the ideal gas law again. PV equals nRT. I personally, yes, we could use the number of moles and the pressure and volume, but I prefer to do it with ratios because I don't like to use a calculator. So if I just write down the ideal gas law twice, and at point A and point B and divide them, then what we find, the N and the R just cancel, and TB is going to be equal to TA times PB VB over PA VA. Nothing here cancels because the pressure changes and the volume changes, but that's going to be 300 Kelvin times, my PB is 4 atmospheres, and my VB is 2 liters, and then we divide by 1 atmosphere times 1 liter. So I don't have to actually use the metric units here because those units are just going to cancel. And so that lets me do some quick mental math, right? We have a 300 times 8, and that's 2400 Kelvin. So that's why I like to do the ratios, because often we don't even need to break out the calculator to get those numbers. And then we can do the same for TC. We're going to have PC DC equals nRTC, and PB VB equals nRTB. It doesn't matter which point I pick. I could pick PA instead of PB VB. I could do PA VA. It would also work. It doesn't matter. But because I picked points B and C, those are related on an isovolumetric curve. So the volumes VC and VB are the same. Those are going to just cancel out. And so TC just equals TB times PC over PB. And that's 2400 times 1 over 4, or 600 Kelvin. So I sometimes like to draw in these isothermal lines and label them. So this is 600 Kelvin, and this one is 2400 Kelvin. It just helps me with the visualization later on. Okay, so all of that is information. It's kind of background information we need to fill in order to solve this problem. If this were a problem on the contest, this might be problem number 1, just to fill in this information. And problem number 2 would then say, well, find the heat input. Problem 3 might say, find the work output and the efficiency, or something like that. I would split it into several problems. And if you can't do problem 1, you can't find the number of moles and the temperatures, but you want to do problem 2 because you know how to do that, then just make up a number of moles and make up temperatures that make sense. Okay, you would have to have an intuition that TB should be hotter than TC and TC should be hotter than TA. But as long as you make up numbers that kind of fit that and then work it out and show me you know how to do it, I would count it as 100% correct. If you make a mistake on problem 1 and you get one of those temperatures wrong or the number of moles wrong, I'll take off points on number 1 for that, but I won't take off points on the later problems because of the earlier mistake. Okay, so you shouldn't be too stressed about that. The only reason I would split this into multiple problems is because this could be a pretty time-consuming problem if it's all one problem, and you just don't have time for that, you know, on a contest. Okay, so we want to find the Q in only, and to help us, we're going to make a table. where we compute the signs of delta U, W, and Q on AB, on BC, and on CA. And the reason we're doing that is because if we go back and look at the first law of thermodynamics and rearrange it, we get Q equals delta U plus W. And so the sign of Q will depend on the signs of delta U and W. We're only looking for when Q is positive because that's when the heat is going into our machine. And anywhere the Q is negative, we don't care about that. That's a Q output, not a Q input. So does anyone remember how to find the sign of delta U? How do we know if delta U is positive or negative? It's very advantageous to us if we know this conceptually, because if we don't, we have to find QAB and QBC and QCA. We have to do all of that work just to find out that we didn't need to do one or two of those. So what tells us the sign of delta U? Let's look at the formula for delta U. So here's our formula for delta U. So how do I tell if that's going to be positive or negative?
The temperature?
Yeah, we just need to know is the temperature going up or down. And even without finding these numbers, I can visually tell when the temperature goes up and down because I've drawn those isothermal lines in. But from A to B, what does the temperature do? Go up or down? Show me with your thumb. Does it go up or does it go down? Okay, goes up. You guys don't like talking. That's okay. That's your product of your age. You can text me the answer. You don't want to say it out loud. Just teasing. Okay, so delta U is positive going from A to B. How about from B to C? Show me with your thumb. Is the delta T, is temperature going up or down? It's down, right? So we get a minus sign. And for C to A, temperature again goes down. Okay, how about the sign of the work? Does anyone remember how to know the sign of the work?
Is it the same thing? Or is it?
It's not, because it's possible that we do positive work, but the temperature decreases. That's possible. They often are the same. They're often the same, but not necessarily. So what we're looking for really is it's positive work when the gas is expanding, right? Because when it expands, it's going to push us and it's going to do work on us. And it's negative work when the gas is contracting. So what's happening from A to B? Is the gas expanding or contracting?
It's expanding.
It's expanding, so the sign of W should be what?
Positive.
Positive. Okay, and from B to C, what's the gas doing, expanding or contracting? It's a trick question, right? It's not expanding or contracting. It's doing nothing, and so the work is zero. Again, another way of thinking about it is you're finding the work is the area underneath that line, and there's no area under a vertical line. And the area under a line moving to the right is positive, while the area of a line moving to the left is negative. So with that in mind, from C to A, the gas is being compressed. It's moving to the left on the graph, and that means a minus sign. And so we can find the sign of Q by just adding the signs of delta U and W. So when I add two positive numbers, I get a positive number. And when I add a negative number and 0, I get a negative number. And two negatives make a I want to hear it. Two negatives make a
Negative.
Negative. Good. Did it make you nervous? Wait a minute. In math class, I was trained 2 negatives make a positive when we multiply them, but good. I didn't trick you this time. So 2 negatives, when we add them together, make a negative. Okay, great. So I only want to find the Q input, and that means I only need to find QAB. Okay, so I only need to compute that one thing. However, what would we call process AB? What type of process is that? It's not one of our 4 processes, is it? It's not. It doesn't look like, it's not constant volume, it's not constant pressure, it's not one of those red isothermal lines, it's not that curvy adiabatic line. So we don't have a formula for Q for this process. So that means we have to sort of sneak in the back door to find Q. And there's 2 different methods we can use. Okay? So we want to find QAB. And there's 2 methods. Method 1. So we know that delta U equals Q minus W. So in method 1, we just find delta U and we find W and we get Q that way. Okay, so that's probably the method we'll pick, but I want to show you a second method as well. And either one works, and they're basically the same amount of work either way. Method 2. Well, we use delta U equals Q minus W for the cycle, for the whole cycle. And we know that that's equal to 0 for a whole cycle. And so Q just equals W. And this is the net Q equals the net W when we're talking about for a whole cycle. So since we're going to find the network anyway, the net Q would be QAB plus QBC plus QCA. And so we're going to find out the network anyway, and QBC is constant volume and QCA is constant pressure. We have formulas for those 2. So if we wanted to use our Q formulas, we could find QBC and QCA and the network, and then subtract those 2 heats from the network to find QAB. Those both work just as well. Okay, so it doesn't really matter. They both really involve us finding 2 pieces of information that we do not need. Okay, in the first case, we find delta U and W for that process, AB. So maybe I should put little to differentiate between these 2 ideas. Or in the second case, we find QBC and QCA. Again, network, we have to find it anyway. So let's do method 1. So QAB equals delta U AB plus work AB. And we'll find delta U AB first. It's just N CV delta T, and N is 0.041. CV, because we said it's a diatomic gas, is 5/2 times R, which is 8.31. And the delta T, we're going from 300 up to 2400, so that's 2100 degrees Kelvin. And we can just multiply that out. That's 1788.7. I mean, we could probably just round it to 1790, but I'll just keep 1 decimal place for each of these numbers. Okay, then we want to find the work. So to find the work, AB, this is not the total work, this is just work AB. We have to, what we're looking for is all of that. So what I would do is find the area of the triangle and the area of the rectangle and add them up. So the work AB is the area of the triangle plus the area of the rectangle. For the triangle, it's 1/2 base triangle, height triangle, and then for the rectangle, it's just the base of the rectangle times the height of the rectangle. So putting in our numbers for the base of the triangle, that's, you know, from 1 liter to 2 liters, that's the difference between these two volumes. 0.002 minus 0.001 is 0.001. So we get 0.001. And the height, we're going from 1 atmosphere up to 4, so it's a height of 3 atmospheres. Or the difference between these two numbers, the difference between 4.052 times 10 to the 5th and 1.013 times 10 to the 5th is 3.039 times 10 to the 5th. Okay, so that's the area of my triangle. And for the rectangle, we have the same base, but the height of the rectangle is only 1 atmosphere. So 1.013 times 10 to the 5th. So the first number is 152. And the second number is 101.3. It's kind of 152.0 and 101.3 joules. So incidentally, the area of that triangle is the network. That's the network of the process anyway. So it's nice that we've computed that. But our work AB then is 253.3 joules. That's for AB. Sorry, not network, just the work from A to B. Is that much? And so the Q AB is the sum of these two numbers, 1788.7 plus 253.3, it's 2042. Okay, and finally, to find the efficiency, that's just the net work over the heat input. And the net work, well, we found it on accident. It's the area of that triangle. It's 152.0 joules over 2042 joules. That's 0.074. Which is 7.4% efficient. All right, so that's kind of like just a sample of a complete problem. This is the type of problem even in your thermodynamics class that you would do. Just to complete, you get seen a cycle, you get shown a cycle rather, and then you find the area of the cycle, you find the net heat input, you find the efficiency. And the last thing that we don't know how to do here is to compare, how to compare this to the maximum possible efficiency. So to do that, we have to learn about a new engine that is sort of the theoretically most efficient engine possible. And in order to do that, we have to talk about what happens when we take a cycle like this and we run it backward. Okay, what happens when we run a cycle backward? So let me kind of repeat that diagram that I showed you last time. I think we saw this right at the very end. So we have a cold place and a hot place. Looks like the flag of the Netherlands, I think. I forgot to look that up and see what flag this is. Does anyone recognize what flag that is? I think if it's on its side, it's France, but like this, I think it's Netherlands. Anyway, and we take a machine and we kind of put that machine here, connecting the hot and the cold places. And when we connect them, you know, what's going to happen is heat is going to start flowing from the hot place to the cold place. So I'm going to just make up some numbers. We have a Q, which we can call QH, and it's coming from this place TH, a temperature TH. And then a heat QC flows into the cold place where the temperature is TC. And in the process, some work output occurs. And let's just say we have 100 joules of heat going from the hot place and 20 joules of work. So that's a 20% efficient machine. And that means there's going to be 80 joules of heat, waste heat, going to the cold place. So if we reverse this machine, then what happens is, let me copy and paste the reversed machine. Okay, so when we reverse this machine, we have now a work input. And the heat is going to flow into the hot place. And it's going to flow out of the cold place. So if we have 20 joules of work input, then we can move 80 joules of heat from the cold place to the hot place. Now this is known, you know, this is a heat engine. And this is what we get when we go clockwise. And this is a refrigerator, which is what we get when the cycle goes counterclockwise. It can be a refrigerator or a heat pump. Your book doesn't seem to talk about heat pumps a whole lot, but it's basically the same machine. An air conditioner or refrigerator have the same purpose. Their purpose is to make your cold place get colder. They do that by pumping heat out of the cold place. A heat pump is the same device, but the focus is different. You want to pump heat out of a cold place into a hot place, but your purpose is to heat the hot place. So the way a heat pump works, if this were a heat pump, you would be pumping in the winter heat out of the cold outdoors into your house. And look at this machine. If we could spend 20 joules of work to net 100 joules of heat in our house, that's sort of a 5-to-1 benefit. That's way better than just spending 20 joules of energy to create 20 joules of heat, which is how we actually do it. Most of us in North America, we're basically still cavemen. We have a fire in a box in the basement, like in our cave. We've got a fire and we burn the fuel and the heat is, you know, released, and then we try to spread that heat out through our cave. So for 20 joules of fire energy, we get 20 joules of heat spread out through our house. A heat pump instead, what it does is it doesn't create the heat, it just coaxes the heat. It encourages the heat to flow from the cold place to the hot place. So when that happens, maybe I should kind of have, this heat flowing from cold into hot. So the blue stuff is the heat flowing from the cold place. The problem, though, of course, whether it's a heat pump or a refrigerator, is that heat doesn't like to flow the wrong way. And when I put the hot place and cold place into contact, what we're going to get is we're going to get heat flowing the wrong way, but we're also going to get some heat kind of flowing back, sort of leaking. Now, if we could design a perfect refrigerator that wouldn't leak, which we cannot do, but if we could make that perfect refrigerator, then this thing we could think of it as an efficiency in some sense of 5 if we are wanting to use it as a heat pump. That is, we get a 5-to-1 ratio of the heat moved into our house versus the work energy that we spend. On the other hand, if we're thinking of it as a refrigerator, so we're really focused on removing heat, it's a ratio of 4-to-1 because we can only move 80 joules of heat out of our refrigerator with an expenditure of 20 joules of work input. So I'm using the word efficiency, but there's a different word for refrigerator or heat pump. It's called the coefficient of performance. And we use the capital letter K for the coefficient of performance. And it's defined if we have a refrigerator versus a heat pump, it's defined a little differently. So for a refrigerator, what we're concerned with is the QC over the work. But we have to be a little careful about the signs of these things because the work, for when we reverse our cycle, the work is a negative number. So we use the absolute value. And the heat, Q cold, remember Q cold is going into our machine, so it's positive. So we don't need an absolute value for QC, although a lot of times people just write absolute value over this whole thing just to not have to worry about it, okay, to not have to think about it. But technically, we only need absolute value on the bottom. If we're talking about a heat pump, then what we're more interested in is the QH, how much heat is moved to the hot place. So this would be QH over W. And the sign of W is negative, but the sign of QH is also negative. So those two minus signs wind up canceling anyway. So you don't need absolute values, although again, sometimes people just put absolute values just to be sure. Because, some people, when they talk about work, they mean work done on the gas, and some people mean work done by the gas. So to avoid confusion, we just take the absolute value of all those things. Okay, so let's figure out how the most efficient engine would work. The idea for the most efficient engine comes from a French scientist named Sadi Carnot, who devised an engine that, if it's reversed as a refrigerator, it would not have any heat leakage. So in that sense, it's a perfectly reversible engine. So what makes a difference between an engine that's reversible and one that you can't really reverse? We kind of reverse it, but it doesn't perfectly work. So the problem is that heat likes to flow spontaneously from hot to cold, and there's really nothing we can do to stop that. If we have a hot place and a cold place in contact with each other, this is just coming from a statistical fact that as the particles interact, if there's any interaction, that on average heat's going to flow from hot to cold just because there are so many particles, and on average as hot particles hit cold particles, they're going to slow down, and the cold particles are going to speed up. So he devised an engine where all of the heat flow that happens not from hot to cold, but from one temperature to the same temperature. Okay, so this is involving the isothermal process. Remember how isothermal works? We want to keep the temperature constant, so we make sure that our environment is that our system is in an environment that is at the same temperature as it, like a water bath. Maybe we have ice water and we have our machine in an ice water bath, and we allow heat to flow into and out of that ice water bath. So the temperature inside our machine is 0 and the temperature outside is 0. That heat flow is not spontaneous. It is not irreversible because of some statistical thing. If the temperatures of both sides are the same, then the heat can flow either way without violating any statistical laws. So he made a reversible refrigerator that's theoretical. We can't actually build this perfectly, but it's a theoretical refrigerator or engine. And then he made the following argument. He said that no machine could be more efficient than his machine, because if we did have a more efficient machine, we could sort of connect them together. Actually, what I'm going to do, I'm going to copy this picture onto another page so that the notes have both images. So he said, suppose I have a machine, my Carnot engine is 20% efficient, and somebody comes along and they make a 30% efficient engine. So we would have 30 being the work output when the heat input is the heat input is 100, and then the waste heat output would be 70. So that's my more efficient machine that someone made. Now, Carnot has his machine, which is reversible and will take 20 joules. So if we put that 30 joules of heat in, actually, let's just take 10 joules of the work and use it for something, and then we have 20 joules left to feed into Carnot's refrigerator. I'm just doing that because the math then becomes easier for me. So there would be a QC flowing into Carnot's engine equal to 80 joules, and a QH equal to 100 joules. So this machine, if they have a more efficient machine and I connect it to Carnot's refrigerator, it then becomes a machine that, look what happens when we run it. Every time I crank it through a cycle, my cold place gets colder by 10 joules, and I get 10 joules of work. And my hot place never gets colder. It never loses energy. So this is a violation of the second law of thermodynamics. And the second law of thermodynamics is a very weird one, because there's not like one unique second law. There are dozens of different versions of the second law that eventually were all shown to be the same. So let me tell you one version. It says that it's impossible to make a machine that has as its sole effect removing heat from a cold place without any work input. So this would be such an example. Another example would be it's impossible to make a machine that just draws heat from a cold reservoir to do work without any heat input. A third way of saying it is that it's impossible to make a machine, and this is probably the most fundamental, it's impossible to make a machine that will reduce the total entropy of a system, of a closed system. So entropy is related to the order or disorder. You may have learned about it in chemistry class, but basically the colder we go, the more order we get. If you think about, ice crystals are very ordered. They have a hexagonal pattern, and there's order there. As they melt, they become liquid molecules, and there's still some organization. As they get hotter and hotter, the disorganization gets larger and larger until eventually they boil. So you can think of it in that way, that the colder things are, the more organized they are. And in this machine, what happens is the cold place just gets colder and without any effect. We could just, instead of taking this 10 joules out of our system, we could just pump it in. I didn't do that because I want the math to be easier on the Carnot refrigerator. But, you know, if we just pump 30 joules in, we're just going to remove more heat from the cold place. And this is a closed system where the hot place never gets hotter and the cold place just gets colder and colder and colder. For now, I want to just show you what the efficiency of Carnot's engine is. This is a very good logical argument that there's a violation of the second law of thermodynamics. Now, a lot of people historically have really sort of fought against the second law of thermodynamics and said, but why can't a cold place just get colder? Why can't it happen? Why can't entropy just spontaneously decrease? So here's an example of entropy spontaneously decreasing. I've got a box of 100 red marbles and 100 blue marbles, and I dump them both into a box that will hold 200 marbles. So first off, they start out very ordered. All the red ones are together, all the blue ones are together. When I dump them, it's probable that we still have large clumps of red marbles and large clumps of blue marbles, but they're probably going to get mixed a little bit. And if I then dump the marbles back into those two 100 marble boxes, they're going to be more mixed. And if I keep doing this process, they're going to get more and more mixed up. Now, is it possible that if I keep doing this process long enough, eventually I get back to a box of red marbles and a box of blue marbles? It's possible, but statistically so unlikely that it will never happen in a billion lifetimes of a billion universes. And that's just 200 marbles. So when you're taking Avogadro's number of particles, this law is a statistical law. It is statistically so improbable that it will never happen. Another example would be just the air in the room that you're in. If you open the window, there's no physical reason why all of the air molecules in the room, they're just bouncing around. They might all just bounce around and leave the room at once, and you're stuck in a vacuum. But the odds of that happening are astronomically small. It will never happen. You could open every window in the world, every planet, every universe, it still will never happen. But it's not because of forces, it's not because of conservation of energy or some other deep principle. It is a statistical law. Okay? If you only have 3 red marbles and 3 blue marbles and you dump them and you keep, sometimes you will get just 3 red and 3 blue back, okay? But as soon as you get like 100, already the odds are astronomically small. So the second law, people have tried and tried, well, but can't we, and tried to find ways to make perpetual motion machines. This would be an example of a perpetual motion machine. You could keep something moving forever, and the cold place just gets colder and colder and colder, you know, and you don't have to spend any energy to do that. Okay, so, but let's see if we can understand what his machine is and what its efficiency is, and we will use that as our limit. Then we can all go on to watching the Champions League semifinal, which is, I'm sure, what you guys would rather be doing. Okay, Manchester City versus PSG. So here's Carnot's engine. It starts with an adiabatic expansion. Sorry, this one's isothermal. And then it goes to an adiabatic expansion. So let me draw some isothermal lines. It's not a very good one. Then it contracts isothermally. And then it has an adiabatic further contraction. So we have points A, B, C, and D, and these two are adiabatic. So why is it reversible? Adiabatic has no heat flow, right? So the only thing that makes something, this is reversible. The only thing that would make it irreversible is if there's heat flow from hot to cold. Well, on the two adiabatic segments, there's no heat flow at all, and the other two are isothermal. So that's heat flowing not from hot to cold, but from hot to hot and then from cold to cold. So this is a perfectly reversible engine. How do we find its efficiency? So conceptually, what happens here is we have a heat flowing in here. We could call that the Q hot, and heat flowing out here, we could call that the Q cold. And we know for the cycle, delta U equals 0. That's Q minus W. And so Q just equals W. This would be the net Q equals the net work. And the net Q would just be QH plus QC. So without actually having to integrate this thing, we have a formula for the Q, the work based on the Qs. Now the efficiency is equal to the net work over the heat input. The heat input is just my QH. So that's QH plus QC over QH. And we could express that as just 1 plus QC over QH. Okay, so we really only have to find the QC. That's what's going on when I go from point C to point D. And then the QH is from A to B, and the QC, which is from C to D. So how do I find those heats? Well, remember, if we go back and look at our review, for isothermal, the Q is equal to the W, and the W, we have a formula that we got through direct integration. So the value of Q is nRT times the natural log of the final volume over the initial volume. So I'm going to use that. My QH is NR times TH times the natural log of V final. I'm looking at segment A to B, so the final volume is VB over VA. And the Q cold is nRT, we could call it T cold, times the natural log of VD, my final point is D, over VC, the initial volume. So the efficiency then is 1 plus nRTC natural log of VD over VC divided by nRTH natural log of VB over VA. The N and the R just cancel out. Okay. Let me pause because I know this is just another level from what we've done the rest of the semester. Are there any questions? Okay, right now, this is looking a little funny. It's looking like the efficiency will be bigger than 1. But we have to keep in mind that natural log is negative whenever the argument of the natural log is less than 1. So if I look at VD over VC, the volume D is smaller than the volume C. So on the top, this is going to be natural log of a number less than 1. It's going to give me a negative number. And on the bottom, VB is bigger than VA. And so we're going to get natural log of a number bigger than 1 or a positive number. So ultimately, we get a negative number out of this thing. Now, the last thing for me to show is that this ratio of the natural logs actually just turns out to be -1. Okay? So that our final answer is going to be 1 minus TC over TH. Okay, that's what I'm going to prove to you. But it takes a little doing to prove how those ratios are related, okay? So let's see if we can do it. We want to find the ratio for VD over VC. So I'm going to use the ideal gas law, P D VD equals NR TD, and P C VC equals NR TC. And I'm going to just divide those two equations. Well, maybe that's not what I want to do. Yeah, so what I want to do is I want to show how the VD over VC ratio is related to the VB over VA ratio. We know that the N and the R cancel, and TD and TC are the same because that's an isothermal line. So that tells me that PD VD over PC VC equals 1. And we can use the same logic on the other ratio, VB over VA. So P B VB equals NRTB, and PA VA equals NRTA. So when we divide those, since TB and TA are the same, we get similarly PV VB over PA VA equals 1. I know I need the adiabatic legs, so let me just write them down and see how it works. So P B to the gamma for part A equals P B to the gamma for D, and PC VC to the gamma equals P B BB to the gamma. So what I'm doing here is I'm looking at the adiabatic legs, and I'm just dividing the equation. So the leg A to D has the equation PV to the gamma equals constant. And yeah, so by dividing those, what we can do is we can relate the PV, we can factor out one of these V's. So we have PA VA times VA to the gamma minus 1 over PB VB VB to the gamma minus 1 equals PD VD times VD to the gamma minus 1 over PC VC times VC to the gamma minus 1. Okay, so yeah, this is what we need to do. And because PD over VD is equal to PA over VA, I can cancel those two. So, and then we can also cancel these two. So this ratio is 1, that's there, and this ratio is 1. That's actually what's canceling. So now I have an expression that says VA over VB to the gamma minus 1 equals VD over VC to the gamma minus 1. And then we can take the gamma minus 1th root of both sides, and we get VA over VB equals VD over VC. Okay, good. That's what I'm trying to prove. So how does that help me? Because we have this expression and if you notice, the top ratio has VD over VC, so D is on top, C is on the bottom. The bottom ratio has B on top and A on the bottom. So if I use this relationship to substitute, I get the natural log of VA over VB divided by the natural log of VB over VA. So we can think of this VB over VA, let's write it again, VA over VB as a natural log of VA over VB to the minus 1 power. And if we have a natural log of something raised to a power, we can pull the power out in front. So this is a natural log of VA over VB divided by minus the natural log of VA over VB. And so the natural log stuff now cancels out, and we just get -1. Okay, so let me recap that. So I should have started with, that's why I got thrown off. I should have started with the adiabatic curves. And then with the adiabatic curves, what we really want to show is that the ratio of the volumes are related, but these pressures kind of throw us off. But the ideal gas law from the isothermal legs allows us to eliminate the pressures. And so then we get a relationship just showing us that the ratios VB over VA and VD over VC, those are the same ratio, except one of them is flipped relative to the other. Therefore, the natural logs ratio just gives us a -1, and that then gives us the efficiency of the Carnot engine. All right, so we don't have to prove this again, but we want to be able to use this result. If we have a Carnot engine, then let's take a look at our first example that we did. We had an efficiency of 7.4%. What would the efficiency of a Carnot engine that worked in the same temperature range be? This runs between 300 Kelvin and 2400 Kelvin. So the max efficiency, which is the Carnot efficiency, would be 1 minus TC over TH. That's 1 minus 300 over 2400. That's 0.875. Or 87.5% efficiency. So this 7.4% is still bad, because the theoretically most efficient machine would be 87.5%. efficient operating between these two temperature extremes. However, if we found out that the maximum efficiency between the temperature extremes was, say, 10%, then I would say this isn't so bad. So how can we get a lot of efficiency? How can we get a high efficiency? Well, we get a high efficiency when this ratio is small. How do we get a small ratio? Well, if TC is very cold, okay, if we could get absolute zero for our cold place, even deep space, far beyond our solar system, the temperature is maybe 2 to 3 degrees Kelvin, just because of the radiation that's sort of passing through the space. But if we could get an absolute zero temperature, then we could have a 100% efficient machine. Alternatively, if we have a very high temperature of the surface of the sun is about 5,800 Kelvin. That is high, but it's not infinite. So if we were going between deep space and the surface of the sun, we would have 1 minus 2 over 5,800, which is 99.97% efficiency, but still not 100. All right, so that's how the Carnot engine works. We will, when we're solving problems sort of as a last step, sometimes we're asked, how does the efficiency of this machine compare to the maximum theoretical efficiency? And that just means, what's the Carnot efficiency between the whatever's the hottest temperature in that problem and the coldest temperature in that problem. And once we find those temperatures, we can easily find the Carnot efficiency.
Okay, so let's try a problem. Suppose we have a cycle that starts at a point A with a volume of 0.02 meters cubed at 1 atmosphere, and let's just kind of stick with 300 Kelvin for the starting temperature. And the pressure increases isovolumetrically up to 3 atmospheres. And then we're going to have an isothermal expansion back down to 1 atmosphere. And then an isobaric compression bringing us back to point A. And we want to know what is the net work input, what is the total work from the cycle, what is the net heat input and the efficiency, and finally we will compare this with the Carnot engine. So we need to know what kind of gas it is. Let's say it is a monatomic gas. And probably the first thing we need to do is fill in some blanks. We don't really know what the temperatures are at any point other than A, and we don't know what the volume at point C is. So we're going to use the ideal gas law to fill in a few blanks, and then we can try to solve some things. So first of all, let's try to find the temperature at point B. We do that using the ideal gas law. PV equals nRT, and we write it twice. Remember, that's the trick. And And since I'm trying to find the temperature B, I'm going to put the B's on the top. And I'll put A's on the bottom. Then we divide these two equations. When we do that, the N and the R cancel. And looking at the segment from A to B, that is constant volume, so the volumes will also cancel. And we find that TB is equal to TA times PB over PA. So that's 300 Kelvin times 3 atmospheres over 1 atmosphere. I don't need to convert the units into pascals here because they're going to cancel anyway. And so that gives me just 900 Kelvin. And we know that TC, because points B and C are connected along an isothermal line, they're at the same temperature, so TC must also be 900 Kelvin. Okay, so we fill those in. Now we know the temperature at each point. Let's write those in. We have 300 Kelvin for this isothermal line and 900 Kelvin for the next isothermal line that we've drawn. Now we know the pressure at points A, B, and C. And we know the volume at A and B. We need to get the volume at point C. So again, we use the ideal gas law. PV equals nRT. We write it twice, stacked on top of each other. I'm trying to solve for VC, so I'll put the C's on the top. And I can pick B because they're connected on an isothermal line, or I can pick point A because they're connected on an isobaric line. I'll just pick A, and then we divide. Again, the N and the R cancel, that always happens. And because I'm comparing points A and C, they are connected by a constant pressure of 1 atm. Those pressures just cancel. And my VC is equal to VA times TC over TA. So that's 0.02 meters cubed times 900 Kelvin over 300 Kelvin. It's going to be 0.06 meters cubed. Okay, so I had to do that to fill in all of the missing information. We additionally might want to find the number of moles using the ideal gas law. That's equal to just PV over RT. I can pick any point I want, so let's pick point A. And the pressure is 1.013 times 10 to the 5th. The volume is 0.02. The ideal gas constant is 8.31, and the temperature is 300 Kelvin. So that's going to give us 0.813. In case we need that. Okay, so all of that was just to fill in all of the blanks. Now we want to find the net work. So the net work is equal to the work going from A to B plus the work going from B to C plus the work going from C back to A. We can grab the diagram, copy it onto the next slide just so that we can refer to it. And then we can consider the work from each of these segments. So the work AB, well, that's isovolumetric, so there's no area underneath the line from A to B, so that work is just 0. the work from B to C. This is isothermal. So we worked that out earlier, actually in the last lecture. It's equal to nRT times the natural log of V final, which would be VC, over V initial, which would be VB. The temperature is either TB or TC, they're the same. So we have 0. What was our number? Was 0.813 moles times 8.31. Those numbers are kind of similar, aren't they? Times the temperature. The temperature on this BC line is 900. Then we have the natural log of VC. Our VC was 0.06 cubic meters over 0.02. That's basically just the natural log of 3. I get 6,677 joules. And then we have to do the work from C to A. This one is pretty easy because it is isobaric, so we're really just finding the area. If we want to think in terms of areas, what we just found was the entire area underneath the line BC, and what we need to get now is the area of the rectangle from A to C, and those will cancel out. So the final result when we add these three works together will be just the area inside this almost triangular shape. So the work from C to A, it's isobaric. It's just, the base times the height of that rectangle. The base is 0.04 cubic meters, and the height is just 1 atmosphere. That's 4,052 joules, but we have to be careful because since we are moving to the left, this is negative work. Okay, because we're moving to the left. And then the net work, if we add all of these numbers together, a 0 plus 6,677 minus 4,052 is 2,625. So that is the net work for one complete cycle. Okay, then we have to find the heat input. So we're going to make a little table. Going to have A to B, B to C, and C to A. And we're going to have the sign of delta U, and the sign of work, and the sign of Q. And we recall that delta U equals Q minus W, so Q equals delta U plus W. So finding the signs of delta U and W will help me find the signs of Q. Going from A to B, the temperature increases, so the sign of delta U is positive. Going from B to C, the temperature does not change, so delta U is 0 going from B to C. And from C to A, the temperature goes back down, so we get a minus sign. Looking at the work from A to B, it's isovolumetric. There's no area underneath the vertical line, so we have 0 work. From B to C, it moves to the right, so there is positive work. And then from C to A, it moves to the left, so there is negative work. So the Q is the sum of delta U plus W. If we add a positive number and 0, we get a positive number. 0 plus a positive number gives me a positive number, and a negative number plus a negative number gives me a negative number. So that tells me I only need to look for the Q from A to B and from B to C. So let's do A to B first. So from A to B is isovolumetric. So the change, the heat is just N times CV times delta T. And we said it's monatomic, so that's N times 3/2 R times delta T. And we can put in our numbers, 0.813 times 1.5, that's my 3/2, times R, which is 8.31. And the delta T, we're going from 300 up to 900, that's a delta T of 600. And that's 6,080 joules. Okay, so how about going from B to C? So B to C is isothermal. We remember that delta U, which is equal to Q minus W, delta U is equal to 0 for an isothermal process, since the temperature doesn't change, and that means the Q BC is just equal to the work BC, and we already computed work BC. It's 6,677 joules. Okay, so the total heat input is the sum of these two numbers. That's 12,757 joules. Now we're ready to find the efficiency. The efficiency is equal to the work, the net work, over the heat input. My net work was 2625, and the heat input is 12,757. That's 0.21. It's 21% efficiency. And compare that with the maximum efficiency given by the Carnot efficiency, 1 minus Tc over Th. The Tc, the coldest temperature, is my 300 Kelvin. And the hottest temperature is that 900 Kelvin. So that's 300 over 900, that's 1/3. 1 minus 1/3 is 2/3. So we could say that's about 67% efficiency. That's the best we could get between these two temperatures. 66 or 67% efficient. So this particular cycle is roughly 1/3 as efficient as the theoretical maximum. So still not too good. Okay, hopefully that gives you an idea again of the complete rundown of a problem. This is what you should prepare yourself to do on the final. You should see something along these lines. One complete cycle, and that cycle will be split up into multiple problems. The first problem might be to do what we did here and fill in all of the temperatures and volumes and number of moles, all the things that we don't know. That could be one problem. Another problem might be finding the total work output. Another problem could be finding the heat input, and then finally another one finding the efficiency, and then comparing that with the Carnot efficiency. So if you find yourself getting to these problems and you blank and you think, oh, I don't remember how to find the number of moles. Okay, well, just make up a number of moles and say, I don't know how to find that, but I'm going to make up a number so that I can continue with the next problems. And I won't take off points on those next problems. So maybe you can't find these temperatures and VC and number of moles. That does not mean you cannot do the rest of it. You just need to make up, if you get in that situation, make up some reasonable numbers so that you can then continue working and show me that you know what to do. And I will not sort of double deduct points because you made a mistake in the first problem and then you used bad numbers in the second problem, and so I take them off again. I won't do that. If I take points off on the first part here, then after that, maybe you made some mistakes, but after that I will grade your work as if all of the numbers you're inputting are correct. And as long as your work is correct, you can still get full credit. All right, so that concludes Engineering Physics 1. Good luck.